Hello, class. So in the previous video, we were talking about the case in which the characteristic polynomial for a differential equation, second order homogeneous differential equation with constant coefficients, had one real root of multiplicity 2. And we saw that from that one real root, we got this solution. y1 equals e to the rx. And we can find what r is because we saw that the differential equation having one real root, only one real root, was equivalent to b squared being equal to 4ac. And we can just plug that in into the quadratic formula to get r equals negative b over 2a. So we got this one solution. Then we talked over this theorem, right, the reduction of order theorem, that told us that if we have one solution for a second order homogeneous ODE, doesn't have to have constant coefficients, so it's even more general. As long as we have one solution with interval of definition I, we can use this formula to find a second solution, which is going to have the same interval of definition as the first one, and for which y1 and y2, so the two solutions, are going to be linearly independent on the original interval of definition. This was the reduction of order theorem. I mentioned that I'm not going to prove it. You can see the proof in the book in either section 3.3 or 3.4. So let's go back to our work. We already have this one solution, e to the rx. We know what its interval of definition is. It's negative infinity to infinity. So we can use the reduction of order theorem to find another solution with the same interval of definition, and which is going to be linearly independent with y1 in this interval, which is all real numbers. Okay. So let's go ahead and do that. So by theorem 1, the reduction of order theorem, y2 is going to be equal to this messy thing, right? y1 times the integral of e to the negative integral of p of x dx over y1 squared, right, dx. So we'll go ahead and plug everything in. The first thing to do, though, is remember that in the theorem, this p of x came from after we divided whatever was multiplying the second derivative. So we have to do that in this case in order to find what p of x is. So right now we have this differential equation. So we have to divide by a so that we can find what p of x is. And again, we know that a is non-zero because it's second order, right? So we know that whatever is multiplying y double prime can't be 0. So it's fair for us to divide by whatever is multiplying y double prime. So get y double prime plus b over a y prime plus 1 over a c equals 0. And hence, our p of x is b over a, right? Whatever is multiplying the y prime. We know what y1 is, so let's just plug everything in. So y2 equals, so I'm just going to write it as e to the rx for now. We know that r is negative b over 2a, but I don't want to be writing negative b over 2a all the time, right? So I'm just going to write r times the integral of e to the negative integral of b over a dx divided by e to the rx squared, taking the integral of all of that. Right, so let's just simplify as much as we can. So we get e to the rx times the integral of e to the negative. Well, what's the integral of b over a? B over a is a constant, right? So we just get b over a x over, we're squaring an exponent, so it's the same as multiplying the exponents. So here we get 2rx dx. Okay. Now, here, I want to use something that we had before. So, specifically, what we know that r is. So we know that, so in this case, I'm going to write what r is explicitly. Again, I'm not writing it here because I don't want to be writing negative b over 2a all the time. But we know that r is negative b over 2a. Now what I'm going to do here is multiply both sides by 2, and I get that 2r equals negative b over a. Why am I doing this? Well, I'm doing this for this reason. I can plug that in into this expression. Why? Let's see how I plug it in. E to the rx times the integral. I have e to the negative b over ax. But we know negative b over a is equal to 2r. So I'm just going to replace negative b over a by 2r. Right, so this becomes negative e to the negative, sorry, we're replacing the negative as well. So negative b over a is the same as 2r, so it just becomes e to the 2rx over e to the 2rx dx. And now this is nice because now this simplifies very nicely because we get e to the rx, well, integral of 1, right? E to the 2rx divided by e to the 2rx is 1. Right? Integrate 1, we get x. So we get x e to the rx. And again, the only tricky thing was replacing negative b over 2a with 2r. Sorry, negative b over a with 2r. That's the only thing. But again, that comes from the fact that we know what r is, that r equals negative b over 2a. So what is our second solution? X e to the rx is also a solution on the same interval of definition. So on negative infinity to infinity, and moreover, y1 equals to e to the rx and y2 equal to x e to the rx are linearly independent on the same interval of definition for the original function, which is negative infinity to infinity. So we have a fundamental set of solutions for this differential equation in this case. So I have fundamental set of solutions. And as we know, if we have a fundamental set of solutions, we know what the general solution is. Which is all linear combinations of the fundamental set of solutions. So y of x equals c1 e to the rx plus c2 x e to the rx, where c1 and c2 again are just any constants. And again, this works for all real numbers. This is a general solution on the whole real number line. So let me write on I here. Now, so the general solution on I. So now we took care of two cases. In the case that we have two distinct real roots, we can find the general solution for all real numbers. In the case that we have one real root with multiplicity 2, again, we can find the general solution for all real numbers. Now, the last one is going to be a little bit harder, but it's still doable. Okay, so last one is going to be the case in which we have two distinct roots, but they have imaginary components. Okay, so we're going to do that in the next video.